Hello everyone and welcome back. In this episode, we are finally adding our code for grabbing objects around. In the last episode, we added some local points, and now we are creating these local points dynamically by clicking on a shape, and then we can add a force to our shape, and then we can, throw it around, right? And we can do that for circles and for any other body we have in our simulation. Okay, then let's jump to the code and implement this new feature. Yeah, in the last episode we added the anchor methods. Now I think we first add our method to add force at a point, at a rigid body. And here I'm gonna add a new method for this, and this will be called add force at point. Okay, add force at point. There we go. And here I'm gonna say the point where we want to add a force to, and the force. Here we will calculate first the direction from the centroid to the shape. We can do this by saying sub at point with this dot shape dot centroid. Then we add the force, this dot force accumulator dot add. So we are adding the linear force, because as you saw, the shape is moving in the direction of the force and also it's rotating. So we need to add two forces basically, and this will be the force accumulator for the force accumulator, the basic force, and then a specific torque. And for this, we need to add a torque accumulator too. It's basically the exact same thing like the force accumulator, but for torque. And torque is almost the same thing. So this dot torque accumulator is 0. And now we can add, oh, did I forget something? Oh, no. No, I didn't forget anything. All right, cool. Yeah, then we can say this dot torque accumulator plus equals, we take the direction, say cross, and with the force. And now we have the torque. And then also we can just say console log this dot torque accumulator. Yeah, that's it for adding force at a point. Not that complicated. Though we need to add one thing too to our integration part. It's for the Semi-Implicit-Euler, because we're using this one. We have to reset the torque, like the force accumulator, to 0 again. And we have to calculate the angular acceleration from the torque. And we can do that by using the Semi-Implicit-Euler, or with using the Semi-Implicit-Euler like this. We are calculating the rotational acceleration. It's again the exact same thing like with the other acceleration for the normal force. Yeah, I'm gonna say this dot torque accumulator times this dot invert inertia. Like here we said we did it for the mass, for the invert mass. Here we're gonna use the invert inertia, and now we can add we can convert this rotational acceleration to the angular velocity. We can do this by just multiplying the rotational acceleration with the delta time. And yeah, and then we get our delta rotation from that. I'm gonna implement these two lines for the other integration methods too in the next episode. The Ranji Kuta 4, I think we actually need to do, we need to do all of these things here again, just for the rotational part. Yeah, but I'm gonna do that in the next episode. All right, then we have this one. I think that's everything we need for the rigid body class. I think we can go now to our simulation class to add the logic for grabbing objects. And I think I'm gonna do this right under the console log, right below the console log, and I'm gonna say this dot selected rigid body is equal to null. Then we have another method called this dot selected position is equal to null. And then we have this dot selected anchor ID is equal to null. All right, then in the same in the constructor still, I'm gonna add I am going to remove this line, and I'm gonna add I need to add two circles. So this dot rigid bodies dot push new rigid body, of course. It will be a circle shape with a position of 500 and 300 with a radius of 60 and with a mass of 1. Then I'm gonna copy that, paste it in here, and set the coordinate for this one to 600 and 300 and the radius to 30. Same mass. Actually, I can use a smaller mass. Do it like this. Okay, and then we have this one. I'm gonna set the mass of the other rectangle to 1, 2. Yeah. Okay, that's everything for the constructor, for our initialization. Then we're gonna add a new method, and I'm gonna call this one, I'm gonna do that below the create boundary, and I'm gonna call this one handle mouse object interaction. And here I'm gonna say if the mouse from the left button is down, so mouse down left, I'm gonna retrieve the, okay, this is going to be a little bit difficult to understand. And I think also I need to add, I need to add some more methods to our grid class, because I need to get the contents of the cell. Okay, spatial grid, right? That's actually, it's not that much, luckily. We just add a new method in the spatial grid class, and we're gonna say here get content of cell, and I'm gonna say the ID, and I'm just gonna return this dot cells with the ID. And I think for the hash grid it's going to be the same. Yeah, I might need to add another method here. Yeah, I need to implement this method in the other way for the hash grid, but I'm not really done in the spatial grids now. I need to add another method, and this will be get grid ID from a simple position. Yeah, I'm gonna pass here a position, and then I'm gonna calculate the same thing like we did right there, but only using the parse int things. No. So I'm gonna say let x is equal to parse int position.x divided by this cell size. Same thing for the y position. So what we're doing here is we are getting the grid index from a simple position, and can here return the here our index for our one-dimensional array. And we need to do the same things for the hash grid too. So I'm gonna copy this one. Then I'm gonna go to the hash grid. Where did I put that? Right under the map to bodies. I'm gonna do that right there too. And here, the get content of cell. That's a bit more complicated. First, I'm gonna retrieve the content. So this dot hash map dot get with the ID, and if the content is null, then we return a empty array, and if it's not null, we're gonna return the content. Okay. Good. Then the grid ID from position, this is also a little bit different because we're using the cell index to hash. Actually, we can still use this one. I just have to modify this line, and this will be cell index to hash with x and y. And I hope that's now everything we need. Alright, then let's go back to the simulation. If the mouse is pressed, then we're gonna retrieve the grid index from the current grid. So this will be this dot grid dot get grid ID from position, and this is the mouse position. So mouse position. Then we can get the bodies which are near from our mouse position. So I'm going to call this near bodies is equal to this dot grid dot get content of cell, and here we can say the ID of the cell. All right, and then we can iterate through all of the bodies. The bodies length plus plus. Yeah. Okay, yeah, we need to add another method. Because of course we need to check if our mouse is actually inside the body. So mouse inside is equal to near bodies shape is point inside. And here I'm going to say mouse position, and we need to implement this is point inside method too. All right, then let's go to the shape. I think Let's go to the shape. Maybe we need to implement this one in every other shape. For example, in the polygon class. 1 second though. Okay, our method point inside. Yeah, we need to go to the shape class, and here we also need to add a new method, and this is point inside with a position. Here we say we make a variable is inside, set it to false. Then we have a for loop, and with this for loop we go over every vertice. So that I is equal to 0, I is smaller than this dot vertices dot length, I plus plus. Then we retrieve the current vertex. This is this dot vertices. Then we retrieve the current normal. This is this dot normal. I think normals, right? Yeah. Okay, then we're gonna do a direction vector. So from the vertice to the point. And this is the subtraction of vertex from position. So position and vertex. Then we do the dot product, and we're checking if the dot product from this direction vector with the normal is greater than 0. And if it's greater than 0, then the mouse position is outside of the shape, and we can return false. And if it's not, then we can return. We will return true. Okay. Yeah. The result of the dot product is vert to point dot normal, and if the dot product is greater than 0, we return false, and if not, we're gonna set is inside to true, and after the for loop we're gonna return is inside. Yeah. Alright, and this is our method for is point inside. Cool. And I hope now we have everything. So go back to the simulation. Now we can get if a mouse is actually inside a body. And now we can say if the mouse is inside a body and this dot selected rigid body, if the current selected rigid body is null, so we don't have any selected body, we're saying this dot selected rigid body is our is our current body with our mouse, you know, the current touched mouse with the current touched body with our mouse position. We're gonna say this dot selected position is our current mouse position, but a copy of that. We don't want to change the mouse position itself. Just want to have a copy of the position. Then we have to do something a little bit weird. We have to convert the mouse position and then, the mouse position to a local position to add a anchor. So I'm going to say here I comment to local position, and we can calculate this by local pos is equal to subtraction of mouse pos and near bodies, get shape centroid. Now we have the local position. Yeah, and now we can say selected anchor ID is near bodies, again with the current index. Let's use get shape function, and create anchor. And here, that's our local position. And now we have our selected anchor. Okay, and what if the mouse on left is false? So we are not pressing our mouse anymore. Well, we're saying if this dot selected rigid body is unequals null, so we have a selected rigid body, then we say this dot selected rigid body dot get shape, and we're saying remove anchor from this dot selected anchor position or anchor ID, I mean, yeah. And then we say this dot selected rigid body is null. After the if, I'm gonna say this dot selected anchor ID is also null. We removed the anchor ID. We can now set the selected anchor ID to null, and also we can say that this dot selected position is also null. Okay. Yeah. Now we need to, of course, add our handle mouse object into action. I'm gonna do that in the update method. And I also, oh yeah, I forgot something. We need to add after the if else statement, we also need to add another if statement, and this is if this selected rigid body and this dot selected position is not null, then of course we want to add a force to it, okay? So let's do that. Yeah, let's start. The start position is this dot selected rigid body dot get shape dot get anchor pos with this dot selected anchor ID. Then we are creating a force, a really simple force for just a direction vector from the mouse, from the centroid, from the anchor position to the mouse position. And this is just mouse pos minus the start position, which is the anchor position. I think I can say anchor position. Well, I don't want, yeah, I think I can say anchor position. And then I'm gonna say this dot selected rigid body at force at point. Here I'm gonna say anchor position with that force, please. And I'm gonna draw a line, a debug line. Draw a line this with the anchor position and the mouse position. And it's going to be black, please. All right. Yeah, we also need to change something in the main HTML. And here we need to change this mouse position. That needs to be a vector now. So I'm gonna change first this one here to a vector. So new vector 2, 0 vector, and here I'm gonna say new vector 2 and replace the these round braces with, yeah, I'm just gonna use a vector, all right, instead of an array. All right. Yeah, I guess it's not gonna work. Let's see. Oh yeah, and I also forgot, we need to add a new method in the shape class too to our anchor things, and this is the get anchor position I added a couple of minutes ago. So get anchor position for the ID. And here I'm going to return this dot anchor points dot get with the ID. Of course, we can again check if the anchor is actually there, but I'm not going to do this for now. Okay, and I guess we can now go to the browser and see if it's working. So let's go to the browser. Make sure you saved everything. Refresh. There we go. Let's try to grab our rectangle. Oh, there we go. It seems to work. Yeah, it does work. Awesome. But of course, it's not going to work for our circles because we didn't implement the circle is point inside method, as you can see right there. Okay, so let's do that too. Let's go to the circle, to the circle shape, and let's implement this method there. Okay, this method is for circles. It's quite easy. Is point inside again, then of course the position. It's quite easy because we just need to create a direction vector. So let's do that. I'm gonna say actually I'm getting the distance from the direction vector directly. So I'm gonna say distance to center is equal to the subtraction, the direction vector from the centroid to the mouse, or from the centroid to the position. And I'm gonna say length 2. And here we're gonna return if this dot radius times this dot radius is greater than distance to center. I think that's it. All right, let's jump. Oh, I think I forgot to switch the screen. Damn it. Okay, what I did, the circle, in the circle class, I just added this method. That's everything. Yeah, sorry for that. I forgot that this time. But I got better. Yeah, I just added this method. And now we have the point inside 2. Yeah, I think I'm gonna change a small thing for the rectangle. And I'm gonna change the rectangle to 10, maybe. Okay, so let's go back to the browser. Yeah, now the circles are not pressing anymore inside because the weight of the rectangle is now higher, so they get pushed more outside. But more important, we can move our bodies around. And also this small one, even though they're so tightly packed and there we go. Yeah, we need to increase the force to move any other body here outside. But yeah, it's working. Awesome. All right, this is everything for this episode. In the next episode, we are adding our joints, or we start adding our joints. All right, see you then.